So my name is Daniel Burrows and I work at Imperial College in their solid state physics group looking at making solar cells. The particular type of solar cells I make don't use the traditional sort of hard silicon technologies that you'll see in your calculators and maybe on roofs. Those are very thick, hard silicon cells. What we use is very thin plastic cells which are flexible and which we call.
With this solution, solar cells can be rolled out like newspapers on a printing press.
These kinds of unexpected discoveries are part of what makes science so exciting. You cannot plan on them, but you're really happy when they happen.
Why would you want to do this rather than using the traditional silicon cells? And the answer is that traditional silicon cells So somebody might ask, why would you want to do this compared to using traditional silicon cells? And so the answer is that ours have advantages because the traditional cells need a special manufacturing procedure, which is a multi-billion-pound cost. These labs that are set up, which only use robots, because any little bit of dust which lands on the cell will end up shorting the cell, and a connection will be made across it, and therefore it won't work. So these silicon plants are incredibly expensive, and we're hoping that ours can actually be made in normal air, and it'll be much, much cheaper. So although our cells won't be as efficient, we won't get as much energy per unit area, they will be much, much cheaper, and so we can make like swathes and cover deserts and power cities that way. So let's talk a little bit about what we do. So what we have is a rotating drum, which has a flexible substrate attached to it. So the substrate, think of it as blotting paper, or something the solar cells can be printed onto. There's a line of ink and a doctor plate, and the doctor plate scrapes across the ink and makes the ink fill in little tiny wells, a little pattern of a printing pattern. And then the paper is rolled across it. So this is actually what they used to print newspapers with, for example. It's a very old technology. We're just refining it and trying to make it very, very accurate, and so that we can print a very, very thin, very flat layer with no bumps and no holes. Any hole in it will destroy it. So that's what we're trying to do, is we're trying to make the inks that are very, very thin, very flat, and very uniform. And so what we have is lots and lots of little tiny micro holes next. And that's something you've got to really think about, is that you're working on your little cog in this massive machine. And there's about 40,000 scientists working on this area right now. So there was a recent convention in America which had about that number of attendees. And so you need to optimize your little cog, but make sure that cog fits into the big machine still. So you're trying to make the best cog, that everybody wants to use your cog. But it's got to be one that also fits in with everybody else's machinery, otherwise nobody will use it. So you've got to somehow find all the inputs to your bit, and also make sure that you give out So we've got all these different variables, and what we want to do is we want to find the optimal variables to make this very thin, very uniform layer with no holes. And so what we do is we hold all the variables, we try and keep them all the same and change one variable. So for example, one day we'll be testing a different type of solvents. So we'll keep all the temperatures the same, all the humidities the same, all the pressures the same, all the speeds, or everything else the same, and then we'll try and test the different ones. And then we take these cells that we make and we put them in our fake sun that we have. We have a lamp that has a filter on it that makes it look like the sun, and we test what we get in terms of results. And then we'll go back and we'll change the temperature. So we'll do 3 runs at different temperatures. And what we're trying to find is the best combinations of temperature, solvents, and all these different variables to make the optimal solar cell. Now, the problem that we have So let's have a stop for a second and think about it as a scientific experiment, because that's what we're doing. We're just running a series of experiments, one after the other. So we need to think about the scientific method to conjecture, to build, to test, and then to improve. When we do this, it's very expensive each time. So we're going to look at the science behind it. We're going to think about really hard about the conjecturing and what we think will happen. So that's a combination of computer models. It's a combination of running smaller scale tests. It's a combination of using databases to look up things like boiling point, surface tension, other things, to look at what might work. Because if you've got 150 variables and each one can change between 1 and 100, you've got, I can probably calculate it, an awful lot of experiments you could do, and you just don't have time for that. So it's really, really important to keep the science in mind about why would it be better to be at 110 degrees versus 90? Why would you want to increase that? What boiling points do you want to be at to have the solvent evaporate but leave this active layer behind?